Another type of mixture is one called a colloid or a colloidal dispersion. So here we have a dispersed substance. It's not called a solute, but it's equivalent to the solute. You have something in the water. It's finely divided in what's called the dispersing medium instead of the solvent. So what makes this different? Colloidal particles are larger than typical solute molecules. Okay, they're small enough to stay suspended. It's not like hot chocolate where if you leave it for a while, all the chocolate settles to the bottom, right? That's not a colloid because it doesn't stay. It'll settle out. Colloids do not settle out, but the particles are large enough that they can interfere with the transmission of light. And so oftentimes a colloid will appear somewhat cloudy. This is different than when we mixed two things and saw precipitate happening in lab, because if you wait after that precipitate forms, the precipitate falls to the bottom, right? And you've got clear liquid above and a solid at the bottom. These particles are small enough that they're going to stay suspended. Particles for colloids are typically 1 nanometer to 1,000 nanometers, which is significantly larger than, say, a water molecule. Colloidal particles, being larger, are actually large enough oftentimes that you can see them under a microscope. And they have a jittery motion called Brownian motion. We looked at this video back earlier in the semester. Let's see if we can not listen to them. So these are pollen grains. What do I do? There it is. So these are the suspended particles, the colloidal particles, and they're jiggling around. Why are they jiggling? Because the water molecules are hitting them. So the analogy I used before is just like a beach ball in a big crowd, right? People hit the ball. And if you're only looking at the ball, the ball just kind of bounces around and and you don't really see the people hitting it, but the ball is bouncing like crazy all over the place. So the water molecules are hitting the colloidal particles. It's called Brownian motion. Soap is an example of a colloidal suspension. And we talked a little bit about soap before. Here's a better picture of a micelle. So here's our sodium stearate soap molecule. It has an ionic head, so we've got these two oxygens here and a carbon, and this is going to have a negative charge and a sodium ion associated with it. This part is all carbons and hydrogens, nonpolar. So when soap is in water, what happens is these nonpolar tails and water don't get along very well, but these polar heads in water get along great. And so what happens is they kind of circle the wagons and they put all of the nonpolar tails in the middle where they can all be comfortable with each other, and all the polar heads on the outside where they can be in contact with the water. And they're like, this is like their deep, dark secret inside. We know you hate this part of us, but we're going to hide it inside. So you get these micelles. So these particles, the micelles, of course, are larger than the soap molecules, right? And so the micelles form colloidal particles. And they stay suspended and don't just merge together into one giant micelle because of electrostatic repulsions between the different micelles, because they all have these negative heads on the outside. So the micelles form, and then they don't really want to get together with other micelles, and so they stay suspended. So if you look at a solution, a soapy solution, a lot of times it'll be a little bit cloudy, right? And that's because of the micelles. They're large enough to reflect the light. Any questions? There are lots of different colloidal dispersions, different combinations of liquids and liquids, solids and gases, etc. So fog, smoke, got both of those in the valley here, right? So smoke would be ash suspended in the air, and fog is liquid, water droplets suspended in the air. If you go out and you stand in the fog and you look at the fog and it's just like there, right? You would think, this liquid water, why doesn't it just fall down like rain? Well, the particles are so small that they can stay suspended. But unlike the humidity in the air that we've got in the classroom, it's humidity 41%. So there's water vapor in the air. Does the air look cloudy? No, because those are individual water molecules, right? So in the fog, you have collections of water molecules. They're small enough that they just don't fall out, but they're big enough that they mess with us being able to see through them. Milk is a colloidal dispersion. Liquids and liquids is often called an emulsion, and it's fat globules in water. So you can actually tell the difference between skim milk and whole milk by looking at it, right? Skim milk somehow looks kind of thin somehow, and it has kind of a bluish cast to it, and whole milk is just like white, right? It's just, you're not seeing through me. What's the difference? The amount of fat. So skim milk has less fat molecules, and so it's not as opaque as whole milk. And this is a great one, whipped cream, very appropriate for Thanksgiving. There we've got air bubbles in the butter fat. The Tyndall effect is this effect that colloidal dispersions scatter light. So a lot of times the colloid will be cloudy. You can just see it's cloudy. Yeah, that's not a solution, must be a colloid. But a colloidal suspension, if it's dilute enough, you may not be able to tell just looking at it that it's a suspension or a dispersion and not just a solution. But if you shine a bright light through a colloid, you'll be able to see where the beam of light goes, because the particles here are large enough to scatter the light. And this one's a solution. The particles are too small to scatter light, and so the light just goes straight through. This is another example of the Tyndall effect. Here we have sunshine streaming in through these windows, and we see these, rays of sunshine coming in. It's hecka dusty in there. That's why you can see the sunbeams, is because of all the dust suspended in the air. Those particles are large enough to scatter the light. So you really don't want that effect in your home. The end.